Next component in transformer model is multi-head attention, that is encoder-decoder attention, which is a crucial part of the transformer decoder. It helps the decoder focus on the most relevant parts of the encoder output while generating the target sequence. You can see the example sentence. So there's a input sentence we considered, which is in English, and this is a translated sentence. Then here the encoder processes the input sentence and generate key and value vectors. Then the decoder receives shifted right version of the target sentence and generates query vectors. So all these things will occur. We'll see all these steps in detail. So coming to step 1, inputs from encoder and decoder. So first, encoder output. What is this encoder output? So here encoder has already processed an input sentence, I love AI, right? So we saw this in the encoder part, and it produced keys and value vectors for each token in the input sequence. Then this decoder receives shifted right target sequence as input, which generates query vectors for each word in the target sequence. So these are the corresponding French words for the words in the sentence, I love AI. And the decoder, so the decoder queries the encoder output using Q from the decoder. Then it computes attention scores between this Q as well as key from the encoder. So how this attention scores are calculated with the help of dot product. Then these scores determine how much focus should be placed on each encoder token and the result. So that dot product result is then used to compute a weighted sum of the value V from encoder in order to generate the next token prediction. So you can see how this dot product is calculated as well as uh, how to compute the weighted sum of V in order to generate the next token prediction, everything in encoder part of the transformer. Then compute attention scores. So here each query from the decoder, that is for the words in the decoder, like the French words J, ador, and IAA, they are compared with all the keys from encoder. So what we are doing, we are taking words, all the words in French, and we are comparing them with keys in the keys from the encoder. So encoder contains all words in English. So we are now comparing this. The comparison is done using dot product. So this is the dot product Q into K power T, which results in attention scores, which determines how much focus the encoder should place on each encoder word. So if you take the word J, it is compared with all the words, all the other words in English, I love AI. And you can see that this J is mostly aligned with the word I, as it is having highest score or highest attention. Similarly, for the word adore, it is compared with all the word scores, and you can see the highest attention score is assigned for the word love. So it means this word adore strongly focuses on the word love in the encoder. Similarly, for the third word also, here the highest attention is for word AI. So this IAA, it strongly focuses on this word AI in the encoder. So this dot product similarity between Q and K, that is Q means word in the decoder, query in the decoder, and keys from the encoder. It determines attention scores. The highest scores means the decoder word is most strongly associated with the encoder word. Then step 3 is apply softmax, where we need to convert all these words, all these scores into attention weights. So softmax normalizes the scores into corresponding or respective probabilities. So if you take the word J, these are the attention weights for all the other words. So the attention scores from step 2 are converted into probabilities using this softmax activation function. which ensures the attention weights sum to 1, making them interpretable as probabilities. So if you take the word J, so here J is more strongly influenced by I from the input. So these are the corresponding attention weight. Similarly, adored. So score is attention weight is more for word love. And for the third word, attention weight is more for the third word in English, that is AI. Then step 4, compute final attention output. So this final attention output is computed using value vectors from the encoder and the attention weights obtained in step 3. So here in step 3, we are taking the attention weights as well as values from the encoder. So this part, we need to take dot product between these two. So we'll see it for the word J. 0.5 into, this is a value vector for the word J. Okay, this is a value vector for the word J. So you need to take dot product with 0.5. Then second weight is 0.3. Multiply that with second vector in this one. Minus 0.4, 0.3, 1.2. And the third attention weight is 0.2. Multiply that with third vector from encoder, value vector. So this is the result. This process is repeated for each decoder word. So for the remaining two words also. This output will be used as input to the next layer in the transformer model, that is feed forward network. And it is repeated for all the other words, decoder words, to generate contextual representation that helps in translation. Next step is multi-head attention, which is an advanced mechanism used in transformers that improves how the model process relationships between words in a sequence. So instead of just relying on one attention mechanism, it uses multiple parallel attention computations, which are also called as heads. Okay. So instead of just using a single set of attention scores, multiple attention heads run in parallel. And also, each head learns to focus on different aspects of the input. So what can be the aspects here? It can be either syntax, semantics, or positional relationships of the input word. Then the outputs from all the heads are combined or concatenated. And at the end, the concatenated output is projected using learned weight matrix in order to create the final attention output. So the output is transformed by learned weight matrix. So we can compare this multi-head attention with a team of experts analyzing a sentence. Say one expert in the team focus on word meanings, whereas another expert focus on grammar and structure, and the third expert focus on long-term dependencies. Okay, all these insights, all the members in a team, they focused on different aspects, right? So all these insights are combined in order to make a final decision. So we can just compare this multi-head attention with that. So this allows transformers like BERT, GPT, and T5 to better understand natural language.